Hello, this is Adele. I'm an associate professor at the University of Melbourne. Um, this is our latest work on building an emulation toolkit for intent-based computing across edge-to-cloud compute continuum. Uh, this is a work which has been done by my PhD students, Negin Akbari at Monash University at the time that I was in Monash. Uh, as many of you may know, smart applications and IoT applications are growing massively, and we are having different types of smart applications from smart home, smart city, in different sectors like transport, in health, in agriculture, and others. So, and all of these applications, they are generating a massive amount of data that should be processed in the cloud or in the edge. And usually mm, it is common that we have applications that they have some components running on the edge, some components on the cloud. And at the end, this will create a compute continuum that we have resources that are scattered across edge to cloud environment. One of the challenges that we faced during our Negin's PhD, and we realized that it might be the challenge for many other people, is that how we can we can test or experiment in a realistic setup for continuum. So putting together a continuum for realistic testing of your application is not an easy task. Think about, for example, an autonomous vehicle application. You have some components running on the onboard unit of your car. You have some base stations on the 5G or 6G, for example, antennas. You have some resources in the cloud, and your application may have microservices running in different places. So definitely, as a developer or someone who develops smart applications, you cannot go in a production environment and test your application. Many people, they don't have access to such scenario, and even testing it in realistic or practical environment is not an easy task. So what are the solutions that are common in our community is using something like simulation tools or emulation tools. But the problem with simulation tools is that they are having some limitations in terms of building realistic scenarios and systems, because we have to make some abstractions and assumptions that sometimes they are limiting the quality of our simulation. There are some accuracy concerns because of that as well. So you are not sure how accurate is your simulations compared to realistic and practical settings. And the most important thing is that uh, simulating network is not an easy task. So, and usually having both computing and networking together, and having network simulators that are giving a very good estimates of network protocols and complexities of the network is challenging. So because of that, in this uh, tool, or in this research, we focused on emulation. So we expect with emulation to have more accurate results. And you know, when you have emulation, because you are having some realistic protocols or computers and things like that, you are running your application in a real time environment, and that will give you a very good insights about what will happen in a realistic, in a real system testbed. So this reduce your deployment risks and also improve the reliability of your application and system. So what actually we did in iContinuum is to put together a bunch of you know, off-the-shelf tools, and we integrated them using some Ansible scripts, which is a complex Ansible scripts that will set up an environment which resembles the you know, real continuum system. And this is designed in a very user-friendly way. If somebody wants to have a realistic compute continuum environment, they can have their own resources, add them to a realistic network topology, and you can run your applications in that environment. This will help people to avoid making a complex task of building a realistic compute environment, and it removes all those complexities. So you can just focus on your application testing and experimentation. You can focus on your maybe some resource management or scheduling techniques you are developing and things like that. The code is available at GitHub at this link. If you are interested, you can easily download it and test it yourself. This is an architecture of our iContinuum tool. So we have different layers from the application layer to the infrastructure layer. In the application layer, we might have some chain of the services, for example, or some DAG for our application that shows all the microservices of the application. And then we have in the infrastructure layer, we have some resources like VMs or VMs in the cloud, some edge devices like Raspberry Pi or Jetson Nano, and your laptop devices, and some IoT sensors like camera or other type of sensors that they generate data. And what actually iContinuum does is, as I said earlier, is an integration of bunch of tools together to build this kinds of infrastructure environment and manage it to allow you to deploy your applications in a realistic environment. So for the network emulation, which is the complex part of the continuum, we are using Mininet. Mininet is a tool for emulating network. We are having software switches and OpenFlow protocols for managing these switches, and you can have a network topology that it can be built based on the realistic settings that you have. For example, a bunch of switches that are connecting your resources. For the network controller, we are using ONOS, which is a SDN software-defined network controller that controls all those networking. If you are interested to have some networking control or traffic engineering and other things, you can use ONOS. Then we have an orchestrator that manages computing node as a worker nodes for deploying microservices and pods in the system. So Kubernetes is managing all the computing resources available in the continuum. We have a sophisticated list of monitoring tools installed at different level as a sidecar in the pod that monitors the microservice, as an agent installed on the switch, as an agent installed on the VMs and other stuff, and they are collecting lots of different metrics for evaluating the system situation or monitoring the system. We used tools like SFlow-RT, Prometheus, and Grafana for these kinds of purposes. And we also used Locust for load generations. Think about that you have lots of sensors. These sensors will generate traffic to your system. So it can be an image from a camera, or it can be a temperature sensor, or whatever sensor is that, and data can be sent to the system for the for processing. Locust has this capability that you can have a central point for sending all the data, or you can have multiple agents sending data from different nodes in the system. From the beginning, when we were designing iContinuum, we had intent-driven scheduling as a core of our research, and iContinuum is providing a platform for ideas that are following intent. So what is intent? The idea behind intent is that we are giving some high-level requirement to the system, and the system will manage to satisfy these requirements all the time. For example, you have some latency requirements for your chain of, for example, services, a service chain that you have for image processing. So you want to make sure your delay, end-to-end delay for this chain is always remaining below some specific amount, or you want to have some privacy requirement that some of these microservices are staying in specific nodes in the system and they are not going outside your, for example, network domain or things like that. Intent can be anything in form of system requirements, from the quality of service to privacy, security, functional aspects. And the role of the system is to make sure that this is always satisfied. As an example here, we have a chain of services for image processing, and it has 4 microservices. These microservices are deployed in a environment that a topology that we have built, as you can see, and then we generate some images by Locust to go through this service chain. Then what we did, we defined an intent that it says that, for example, the end-to-end latency for this service chain should remain below 3 seconds. What we did, we started creating some events in the system that causes violation in the intent satisfaction, and then we are trying to fix it through the system modifications or configuration. For example, at the beginning, we have this deployment of microservices in the system. There is a link between switches 4 and S2, and we are making this link disconnected because we have reactive forwarding protocol activated on our network controller. Network controller automatically finds a new path for sending the traffic between these two microservices, microservice 2 and microservice 3. And as you see, it doesn't allow the response time of the system to go above that target response time that we have. In the second event, we are making some network congestion here in between link 3 and 2, and then this will cause delay or response time to go above that threshold. What system is doing at this point is doing some sort of pushing some flows or traffic engineering stuff into the network to allow to find another route for traffic to avoid this congestion in the system, and it brings back the response time to the level that we were expecting. In event 3, we are increasing the load into the system by changing the parameters of Locust, for example, and then because the load goes up, system performance goes down, and then as you see, the violation happens at around this time. So what system it does to resolve the issue, it makes a new replicas of the bottleneck, for example, microservice, which is microservice 3 in this case, and then it will improve the performance again and bring it back to the level that we want. Thank you so much. This was a very quick overview of our emulation toolkit, which we call it iContinuum. I'm going to show you a quick demo in the next video, and you can see how simple is this tool for building up a very complex environment for experimentation. Thank you for paying attention, and see you on the demo video.